As you know, all the work is done by the students and postdocs, and they are Stanford's best product. We have today several of these students and postdocs that have prepared posters. The posters are out in the lobby, and following these lightning presentations, you'll have a chance to look at the posters and chat with the students. We've asked the students to prepare a slide and a 1-minute introduction to themselves and their research. We've coached them that they shouldn't try to compress their entire PhD thesis into 1 minute. It is really tempting to do so, but they're going to try hard not to do it, and we're going to use some obnoxious alarm on my iPhone set for 60 seconds to provide motivation. So your job is to finish before the alarm goes off. I believe we have all the slides here in order, and I believe we have everyone lined up in the same order. So let's give it a try and see if we can actually make this work. Right, some have 2 slides, but if you have 2 slides, you still only have 1 minute. So, and you can all wind around closer here or reduce walking time or do whatever you want. This is a bit of an experiment. Although these lightning presentations are incredibly popular, we've never tried to do it for this many posters.
So are we ready?
So we will learn this afternoon if this was a brilliant idea or not. So our first student, if my sheet is right and if we're all calibrated, is Abbas Zeroni. Welcome, Abbas.
I'm a 4th-year PhD student in electrical engineering department, and my research is in reinforcement learning and its applications. So today at the poster session, I'll be presenting my work about conservative contextual linear bandits. As you probably know, a lot of practical applications which play an important role in industry can be modeled as a bandit problem, where a decision maker can sequentially place some actions and then see some noisy observations out of the actions. Many algorithms have been proposed to deal with such problems in different situations, and all of them follow a common theme. They try to make a balanced trade-off between exploration and exploitation factors in these problems. And all of them have some initial exploration phase during which they try to explore different actions and try to see different aspects of the optimal. Sorry about that. In order to find the. That's too quick.
Do you know why they're laughing?
Of course. Thank you. Thank you.
Our next presenter is Abigail C. Hi, Abigail.
Hi, I'm Abby, and this is work from the Stanford Natural Language Processing Lab. So what we're trying to do here is we're trying to do automatic text summarization. So we want to take a long piece of source text, let's say a news article, and the example on the slide is Germany emerged victorious in 2-0 win against Argentina on Saturday, etc., etc. And we want to condense that down to something much more concise. So for example, Germany beat Argentina 2-0. So it turns out that if you want to write good summaries, you need to be able to do 2 things. You want to be able to copy words and phrases from the input, from the source text, but you also want to be able to generate new words and phrases so that you can paraphrase. So what we're trying to do here is we're trying to use a recurrent neural network. That's the picture on the screen. We're trying to use a recurrent neural network to do both of those things. So our pointer generator network is able to both point to words in the source and therefore copy them and generate new words. So if you come by our poster, you can find out how we do those 2 things and how we learn which one to do. Thank you.
Thank you, Abby. Our next speaker is Abubakar Abid.
Good evening. My name is Abu Bakar. I'm going to be talking a little bit about linear regression. So we use linear regression all the time to figure out the relationship between input points and output labels. So we asked the question, is it possible to do linear regression if you have input points and you have the labels, but you don't know which label corresponds to which point? So this kind of problem arises a lot, for example, in biological experiments, where you characterize a bunch of points, or a bunch of particles, hundreds or thousands of particles, and you have their characteristics, but you don't know which characteristic originated from which point, because they were characterized all at once. So it turns out the naive way of doing this, which might be to try different permutations to see which gives the best linear regression, it turns out it fails. It's not consistent statistically. So we came up with a better way of doing it, which is both statistically feasible and computationally feasible. So come by our poster, and I'd be happy to tell you more.
Our next speaker is Aditya Grover.
We often hear that we live in the age of big data. We do, but more specifically, we live in the age of big unlabeled data, which presents an plethora of exciting opportunities, as well as a key challenge that we now have to learn probability distributions via generative models over unlabeled data. In this work, we present, for the first time, a meta-algorithmic framework that can learn generative models to an arbitrarily high level of accuracy. So in the representative example that you see, for instance, if we want to learn a target distribution, which is a mixture of 4 Gaussians, we do so by first building an arbitrary base generative model. This generative model makes some mistakes, which we then use as a training signal for learning a new generative model that specifically focuses on the previous mistakes. Combining these via boosting process results in a highly accurate boosted generative model. Thank you.
Our next poster is by Alex Ratner and Ouma Varma.
Cool. So I'm a third-year PhD student working with Chris Ray, who luckily for me likes zingy catchphrases. So my entire PhD is about overcoming what we see as the extremely important bottleneck of getting labeled training data for applying machine learning in practice through what we term weaker supervision. So I'll save basically all the details for the poster, and my animations are gone, so all the suspense is ruined anyway. But the thing we'll be presenting about is a system called Snorkel. It's primarily focused on the problem of extracting structured data from unstructured text, although we're also going to talk to you about some stuff extending it to images that we're doing now. And the basic pipeline in this new model that we call data programming is that instead of either manually creating features or hand labeling training data, the subject matter expert writes what we call labeling functions, which are just generic black box scripts like Python functions. And these label data, and we actually model this in a first modeling stage to sort of learn the relative accuracies of the scripts the user writes, and then stuff happens, which I will tell you about at my poster.
Thank you, Alex. Andre, right? Our next presenter is Andre Notzley.
Yeah, hi, I'm Andres. I'm very excited to be here today, and I have a poster about making constraint solvers, specifically SMT solvers, more reliable and more maintainable. So suppose you have a piece of code that looks like the piece at the top, and you would like to know whether a division by 0 is possible. Well, one way to figure it out is to turn that question into a query for a constraint solver and ask it. But when the solver comes back to you and gives you an answer, well, you can't really be sure whether that is correct because constraint solvers are very complicated. And so we would like to make that those solvers more reliable and more maintainable by using domain-specific languages. And yeah, if you would like to know more about that, please come to my poster. Thanks.
Thank you, Andres. Our next presenter is Avanti Srikumar.
As methods to learn patterns from data become more complex, they become harder to interpret. Deep learning represents the latest in this trend, but its uninterpretable black box nature is a major problem. Say you train a model to predict which DNA mutations will cause a disease. If your model does well, it has likely discovered patterns that we ourselves would like to understand, not possible if the model is a black box. We've developed algorithms to address this limitation. The first, called DeepLift, tells you which parts of your inputs are important for making a given prediction. If we use DeepLift to figure out which pixels we should erase to convert the digit 8 into a 3 or a 6, we find it does notably better than other methods. The second algorithm, Medisco, performs pattern discovery. When applied to genomics, We find it gives far superior and less redundant patterns than alternative approaches, and has even led to novel biological discoveries. Our posters are the first when you exit those doors to the left, my right. Please stop by.
Thank you. Our next presenter is Venom Montessori.
Hello, I'm Venom, and today I'm presenting HOMA, that is a new transport protocol specifically designed for network, data center network fabric. So the two main properties of HOMA are low latency for short messages and high network utilization, specifically at high network loads, because that's where things get complicated. So in our simulations, we show that HOMA can actually outperform both pFabric and pHost that are competitor and similar protocols at performance metrics that are related to latency and network utilization, even at 99th percentile tail of those metrics. So in fact, the main core idea behind HOMA is that we observe that congestion specifically or mainly happens at the top of drag switches near the receivers in data center fabric. And HOMA uses some kind of network, receiver node scheduling to reduce this congestion and uses few priorities to achieve those metrics. So if you're interested, please stop by at the poster.
Thank you. Our next presenter is Charles Key.
Hi, I'm Charles. I'm a PhD student with Professor Leo Gibbous. So we know point cloud is an important type of geometric data structure. It's also the default data type for depth sensors and LiDAR scanners. However, due to its irregular format, researchers usually convert it to 3D voxel grid or render them into images or just extract manually designed features to process it. In this work, we will design a novel neural network architecture that directly consumes point cloud. We will show that our network, named PointNet, can be applied to a wide range of applications. And also, we will show theoretical analysis for our architecture. So please come to our poster if we are interested. Thanks.
Thank you, Charles. Our next speaker is Chuk-Ting Lee.
Thank you. So my poster is about the information theoretic limits of randomness generation. So the classical result by Noof and Yao states that in order to generate a random variable x, one would need an expected number of random bits upper bounded by the entropy plus 2. So we extend this to 3 settings. So first, the distributed generation setting where Alice and Bob would like to generate 2 random variables that are correlated, and you want to use the least number of common random bits. And the second setting is the universal remote generation setting where Bob would like to generate a random variable, but he doesn't know the distribution, so he wants Alice to tell him something about the distribution in order for him to generate X. And the third setting is a channel simulation with random, common randomness. Yeah, so thank you.
Thank you. Our next speaker is Christian Matauri.
Hello to everyone, I'm Christian Matauri, and the project that I'm going to present is oriented to solve a very practical problem. So the idea is that 94% of front-end web-based applications are based on JavaScript. And the technical committee 39 is going to extend the language to provide better performance for multi-core processors. The point is that there are significant safety constraints on this extension. And in this project that consists on apply formal method techniques to the analysis of JavaScript, it's oriented to analyze the main JavaScript engines in order to compare the possible execution and analyze if they are conformance with the formal specification, actually.
Thank you. Our next poster is by Daniel Kang, Virus Abuzaid, and John Emmons.
Video data is growing faster than humans can possibly watch it all. But luckily, deep learning will allow machines to extract semantic information from these videos with near human levels of accuracy. However, systems at scale haven't been built around these methods. partially because they're new, but also partially because they're incredibly slow. Just as an example, object detection runs at 10 frames per second on the latest and greatest NVIDIA GPU, which is slower than real time. In response, we present NoScope, a prototype that queries videos 1,000 times faster than the state-of-the-art. NoScope exploits two key insights. The first is that videos have temporal locality, and the second is that for a given query and data stream, we don't need the full generality of the state-of-the-art networks. If you're interested in hearing how we do this, please come to our poster.
Thank you, Dan. Nice shirt. Can everybody see it? Yes, good. Our next speaker is Danielle Self.
So it can be extremely difficult to detect implementation errors in machine learning systems. If you write a program to sort a list and the program ever returns an unsorted list, well, congratulations, you found a bug. But if you write a machine learning program and it doesn't work that well, you don't really know what's going on. Maybe you needed more data, or you needed more layers, or you have the wrong model. Maybe it's numerically unstable. You don't actually know that there's a bug. And in practice, bugs in machine learning systems can persist undetected indefinitely. But there is another way. Using formal mathematics, we can state precisely what our machine learning system is supposed to do, and we can prove that it does it correctly, finding and fixing all implementation errors in the process without resorting to empirical testing at all. And we show that our approach is feasible by developing a machine learning system certigrade for optimizing over stochastic computation graphs and generating a machine checkable proof that it is indeed bug-free. Thank you.
Thank you. Our next speaker is Ed Quigley.
So just as we often see virtual characters in film special effects, we want to create a digital double for a tree. To do that, we have to capture what a tree looks like and how a tree moves. And for the first half of that, we think about the traditional computer vision problem of reconstruction. However, a tree is kind of a problem case for a lot of standard reconstruction algorithms because we have a very large structure that's potentially non-rigid, that lives in an unconstrained environment, and that has a lot of fine detail that we care about. The good news is that we have a very strong prior, and that we know we're dealing with the tree topologically. So what we're doing is mounting cameras onto a small quadcopter. We're flying our drone around the tree and capturing image data. We're labeling twigs in these images, and we're reprojecting those labels to create a 3D skeleton upon which to build our model.
Thank you. Our next poster presenter is Hng Yi.
Hello, everyone. I'm Erik, supervised by Professor Leo Gibbous. So in the real world, we are really faced with data lying on irregular domains such as 3D shapes, social network, or molecules. This domain can be structured as graphs, which is a universal representation of pairwise relationships. In this project, we focus on a specific domain 3D model represented as shape graph, and we study the problem of labeling graph vertices using convolutional neural networks. CNN has shown its great power in many applications. However, applying a conventional CNN to generic graph is not trivial, since a lot of the optimizations exploited rely on the grid structure, such as weight sharing. So in this project, we propose synchronized spectral CNN, a convolutional neural network framework designed for graphs, and which inherits merits of conventional CNN, such as weight sharing and multi-scale analysis. Please come to our poster to learn more. Thank you.
Thank you, Erik. Our next poster presenter is Asha Singh.
Thank you. So as integrated circuits have gotten more complex, particularly with SoCs, it's becoming harder and harder to actually debug them and catch errors in either pre-silicon verification or post-silicon validation. So what's the reason for this? Well, the problem with standard testing is that there's often an extremely large error detection latency, which is a time between when an error actually occurs to the point at which the error itself is observed. This can be millions or even billions of cycles. And as a consequence, debugging that intense trace or extremely long trace is very difficult. You can't capture all of the data to actually go through it, and if you capture the most recent data, it's really not relevant. So in our group, we've developed quick error detection, which reduces this error detection latency by up to 10 to the 9x in cases where, in an actual industry study that we've used. And this actually enables localization and debug techniques such as symbolic QED, where we're able to find a minimum length trace, 3 to 22 cycles to actually activate and localize the bug to specific submodules. And I'd love to tell you more at my poster. Thank you.
Thank you, Asha. Our next speaker is Gage Hills.
All right, today I'm very excited to tell you about the benefits of using carbon nanotubes for very large-scale integrated digital circuits. I'd also like to thank our collaborators at IMEC, who we've been very fortunate to work with on this project. And what we showed is that using all of IMEC's process design kits for sub-10 nanometer technology nodes, that if you replace all the silicon FinFETs with carbon nanotube FETs, your circuits will run 3 times faster while simultaneously consuming 3 times less energy, resulting in an order of magnitude improvement in energy efficiency for VLSI circuits. So I'm sure you have a lot of questions. If you come to my poster, I'll go over some of the most common questions we get, such as where do these benefits come from, and how do CNFETs maintain these benefits even in the presence of wire parasitics and process variations.
Thank you. Our next poster is by Giovanni Campania, Rakesh Ramesh, and Saila Zhu.
Hi everyone, I'm Giovanni. I'm a third-year PhD student advised by Monica Lam. And yeah, today I'm going to present Almond. You have seen Almond earlier today, so I'll be very brief, but I will repeat that, virtual assistants are going to eat the internet. They will replace all interfaces to all services. And we want to build the best virtual assistant, one that is general, covers all services, respects your privacy, you can actually use it, it works, and it's programmable. And we'll focus on the last part, the programmability and the natural language understanding in our poster, where we compare different techniques and different algorithms, and we show how to collect the data and how our system fares on different tests. Thank you.
Thank you, Giovanni. Our next speaker is James Golden.
Hi, I'm James Golden. I'm a postdoc with Brian Wendell in engineering and E.J. Chicholniski in the neurosciences. ICEP Bio is a computational engine for simulating the eye in the brain. It's the most complete and realistic simulation available for how the eye processes light. It's based on Brian Wendell's ICET Image Systems Engineering Toolbox, and the pipeline for ICEP Bio consists of simulating the scene, the optics of the cornea and the lens, the retinal processing followed by inference with a classifier. With ICEP Bio, we've simulated some cutting-edge physiology and psychophysics experiments, as well as the perception of patients with retinal prostheses, and we're currently testing the design of therapeutic virtual reality environments for patients with diseases of the optic nerve. Thank you.
Thank you. You really did say therapeutic virtual reality treatments, right? A phrase we never thought we would hear, and there it is. Our next speaker today is Jenny Jin.
Hi, I'm Jenny Jin, a third-year PhD student in computer science with Rong Fetco in computer graphics. As you all know, digital characters often wear clothes, and so cloth simulation can be very important in many applications. And my work is on improving the quality of cloth simulation with more realism by augmenting the simulation with higher frequency details, which we learn from real-world data. So first, we propose a new inequality cloth model, which basically have edge compression in the meshes as a surrogate for bending, folding, and wrinkling the cloth. And then the next stage is to build correspondence between these compressed edges and the realistic wrinkle patterns, which we capture from the data. And finally, with this learned correspondence model, we can apply them to any simulation to improve the realism as a post-processing augmentation. Thank you.
Thank you, Jenny. Our next speaker is Johnny Israeli.
Hi, happy to be here. As the cost of sequencing the human genome dropped exponentially from billions to thousands of dollars and soon to hundreds of dollars, it has driven an exponential increase in the amount of personal genomic data and functional genomic data. And in the lab of Anshul Kundachi, we believe that deep learning will play an important role in modeling this data and making sense of it. In pursuit of that goal, we developed Dragon and How to Train Your Dragon workshop to learn and teach about this topic and how to do this kind of work. And we also developed production-level versions of these models. One of them is here, TF Dragon, and I'll discuss in my poster how these models compare with the other models that have been commercialized, how we can make sense out of them, and how they could be used to interpret the connection between mutations and complex disease. My poster is right outside this door. Looking forward to chatting with you. Thank you.
Thank you, Johnny. It's okay. Want me to hold your bag for you?
I'll set it down.
Our next speaker is Kessler Williams Tanner.
Hi, I'm Kessler. I work with James Landay
This research is about how do we help people become better designers. And we're approaching it from a couple of angles. First, we believe that people are better at recognizing design, recognizing good design, than they are at creating it. And so we're exploring how do we change design tools to leverage that ability. And the second is machine learning and artificial intelligence has already begun to change design tools. Often it comes at the expense of user flexibility, and the user loses some control over the design process. And we'd like to maintain the benefit of the technology while still allowing the user to remain in control of the design process.
Thank you. Our next poster presenter is Manolis Papadakis.
Hi, I'm Manolis. I'll be presenting our domain-specific language SEAM for writing local operations on graphs. We support a variety of different graph variants, from social networks to unstructured meshes in scientific simulation. Our goals are programmer productivity, verification, and performance. On the front of productivity, we offer a relational data model for expressing your data structures as tables with pointers substituted by fields. And we offer a language for writing such operations that uses familiar constructs like for loops and if statements, but our system translates that into transactional code. We allow users to avoid maintaining auxiliary data structures by expressing them using the notion of views from databases, which our system maintains automatically. And we also allow custom data invariants, and we can even check both those and memory safety statically at compile time. I'll be glad to give you more details at the poster. Thank you.
Thank you. Our next speaker is Margaret Koehler.
Hi everyone, I'm Margaret Koehler from Mechanical Engineering, and I'm here to talk about a 3D haptic shape display. So shape display is a human-computer interaction device that renders a physical environment for a user to interact with via touch. So based on some actuation techniques from soft robotics, we've developed a fully 3D prototype of such a device you can see in the cube. However, to get the ideal case, which would be an arbitrary set of shapes, you need a large number of actuators, which is a pain to build and it's expensive. So instead we've focused on creating a design algorithm that takes a few target shapes that you're trying to reach and gives you a hardware design that will allow you to reach just those target shapes, but with much fewer actuators than required. So if you want to learn more, I'll be at the poster session. Thanks.
Thank you. Our next speaker is Michael Bao.
Good evening, I'm Mike. I'm going to be talking to you today about digital characters, and in particular, I'll be talking to you about their face. If you watched any recent movie, you'll notice that digital characters are prevalent. In Rogue One, Governor Tarkin and Princess Leia are reproduced digitally at Industrial Light and Magic. And how they do this, as they've mentioned in multiple interviews, is that they have artists create these blend shapes, and then they have a Guy Henry, who is another actor, do a performance, and that performance gets transferred over to these digital faces. These techniques are done via blend shapes and standard computer vision techniques. However, these techniques are imperfect and cost a lot of money because of the amount of artists that have to go back and tweak these performances to match the director's wishes. So I'm going to be talking to you about how we can improve this using simulation models and facial simulation. So if you're interested, come by my poster. Thank you.
Thank you, Michael. Our next poster presenter is Erik.
Hello, everyone. Just as a brief background, task-oriented dialogue deals with the topic of building bots that can converse with humans on closed domains, such as hotel reservation, flight booking, etc. So traditional task-oriented dialogue agents tend to be modularly defined. So really, they're very brittle systems that you have to define every single component through rule-based systems that are very hard to adapt to new domains. Deep learning, on the other hand, has the potential to revolutionize how we build these systems by learning all the relevant information and features directly from data. So in this work, we've developed a new class of models that is able to do away with a lot of the modularity of traditional systems using deep learning and still retain competitive performance on real-world data. Thank you.
Thank you. The next poster is by Nandita Bhaskar and Pulkit Tandon.
Hi, everyone. I'm here to pitch my work on brain-machine interfaces and our group's work on brain-machine interfaces. As you know, Elon Musk is into this now. And we work on retinal prosthesis, where we try to provide artificial vision to people blinded by the loss of their light-sensitive, that is, the photoreceptor cells. Fortunately for us, the rest of the neurons in the neural pathway to the brain remain functionally intact. So what this means is that we can now go and electrically stimulate those cells, and if we know the retinal code, we can potentially make the brain see. There are current existing prostheses that do not take into account the intricate cell-type specific architecture in the retina and provide extremely poor vision, actually below the legal blindness limit in the US. So we have some exciting results, first-pass results in our poster. So please come by and talk to us, where we try to give a closed-loop specific design. Thank you.
Thank you. Our next speaker is Neil Jean.
Hi, I'm Neil. I'm a third-year PhD student working with Steph Rahman. So I think at this point, everyone basically accepts that if we have lots of labeled data, we can train deep neural networks to do a lot of crazy things. But there's also a lot of problems where it's fundamentally hard or expensive to collect labels. So in our group, we're working on some semi-supervised approaches that allow you to use unlabeled data to supplement your small labeled data sets in training these deep neural networks.
Thanks, Neil. Our next poster presenter is Nikhil Garg.
Hi, I'm Nikhil. I work with Ramesh Johari in the Management Science and Engineering Department. And so a lot of modern online marketplaces depend on reputation systems. So if you have an experience on Lyft, eBay, Airbnb, whatever, you're asked to rate things after you have it. And it turns out in the last 10 years, a lot of work has shown that these reputation systems are close to useless. And that's for a lot of reasons of how humans behave. We argue in this work that these systems should switch to using comparison-based systems, and because they recover more marginal information per rating and are much more robust to the standard characteristics you see in online markets. For more information, come by our poster.
Thank you. Our next poster is by Nitish Padmanabhan.
I'm Nitish. I'm a student at the Stanford Computational Imaging Lab, and we're working on some perceptual conflicts that are present in virtual reality. One such perceptual conflict is that between vergence and accommodation. Vergence is when your eyes converge to look at an object, and accommodation is when they focus to bring that object into a sharp image. And in the real world, these are linked together, but in virtual reality, what happens is that you are forced to focus to one specific plane, and this leads to eye strain and headaches over time. And so we're working on adaptive focus displays that can recouple these two cues and both reduce these conflicting issues, and for some users, especially older ones, actually make virtual reality in a way better than reality.
Thank you. Our next poster is by Painway.
Hi. So in any machine learning system, a natural question to ask is, why did a model make a given prediction on a given input? One approach is to explain the prediction in terms of the model parameters, but where do these parameters come from? In our work, we trace the prediction of the model back through the learning algorithm and to the training data. In particular, we describe a technique for finding the training examples that were most responsible for any given prediction. This works on any differentiable black box model, and we think it will help end users better understand the models they work with. It also turns out that when you understand the link between the training data and the prediction, you can construct efficient training set attacks. Small changes to the training set that can drastically change a model's prediction. I'm going to leave you with this slide, and to find out more, please come by our poster. Thank you.
Thank you. Our next presenter is Peter Kairos.
All right, so the number of devices that are connected to the internet has recently surpassed the human population on Earth. In fact, this number is projected to grow from tens of billions to trillions within the next 2 decades. Now, this super exponential increase in connectivity presents an unprecedented challenge to lots of wireless system designers and circuit designers. It actually requires a radical reduction in cost and size. In our recent work, we built the first fully integrated IoT radio that is 300 times smaller and 1,000 times cheaper than state-of-the-art Bluetooth low-energy radios. And in order to do so, we had to fully let go of batteries and integrate the clock and antenna on chip. We had to also completely rethink the design of the physical layer and medium access layer protocols. Now, if you would like to know more about our work, or you get bored by all the neural networks talk, please stop by.
Thanks, Peter. Our next poster is by Robert Conrad and Donald Dansero.
Hi, this is work from the Stanford Computational Imaging Lab between myself, Robert Conrad, Donald Dansero, and Gordon Vetstein. So emerging virtual reality systems today are creating unprecedented experiences, breaking the barrier between the real and the digital. And cinematic virtual reality pushes this further by allowing us to capture real-world content and then later displaying it and viewing it in these VR headsets. But capturing virtual reality real-world content or real-world content for virtual reality isn't trivial. Today's technologies capture high-resolution videos from multiple cameras and then end up actually throwing away most of the data via extensive processing before we can actually view it on a VR headset. And this processing can take between hours, days, and even weeks, not leading to very streamable or live applications. We present Vortex, a mechanically rotating camera design that allows us to directly capture into a viewable format, the omnidirectional stereo format, and at the same time actually reducing a lot of the artifacts. Please come by our poster to see how this works. Thank you.
Thanks, Robert. Our next poster presenter is Robin Betts.
Hi, I'm Robin Betts. I'm a third-year PhD student in the biophysics program and a member of the Ron Dror group. And I have a little bit of a departure from the deep learning you've been hearing about to present kind of different machine learning methods that can be applied to interesting molecular mechanisms. So I could focus on figuring out how drugs bind to proteins using all-atom molecular dynamics simulation. Unfortunately, you can't just simulate until it binds, so you have to teach a computer what interesting means in a really biological context. And as for how exactly I did that, you'll have to see my poster. But I have some very exciting results involving how opioid antagonists bind. This work is really interesting as pain medicines are currently not very good, and hopefully using my method as well as others' research, we can make those better. Thank you.
Thank you, Robin. Our next poster is by Xiyu Liu, Yilong Gang, and Ji Yin.
Hi, everyone. I'm Zi, and I'm presenting our work in network telemetry. Suppose we have a very complicated network, and we want to know what's going on inside the network. Currently, we have two solutions. One is a switch-centric, and the other one is a NIC-centric. In the first solution, we can have the switches we can have counters on the switches and let the switches report, say, so 10 times per second of the counter values. But this method is very costly, meaning we have to upgrade our hardwares. And also, it doesn't always give us the information we want. Our approach is the second one, the NIC-centric. So we collect all the tap-in, tap-out timestamps for the probe packets, and we can reconstruct the network from the edges. And also, we have a visualization system telling us the exact conditions of the network. So please check out our posters. Thank you.
Our next speaker is Stephen Yang.
Yeah.
No.
So, it's me.
It's you.
Yeah. Yeah. Yeah.
Oh, I see. We have two posters in a row.
Yeah. Unfortunately, I'm
with the same three students.
Yeah, I'm representing my two missing buddies.
Got it. Oh, and in fact, you are Ji Yin.
Yeah.
Perfect. We have Ji Yin again.
Yeah. Yeah, that's right. It's me again. In this poster, we are introducing our work on how we synchronize clocks in the data centers. As we all know, time is money, so that's something we don't want to mess up with. And also, this clock synchronization problem is very hard. There are existing solutions, but most of them are either not accurate enough, or they are based on very expensive hardwares that are not easy to install in our current data centers. So what we are doing, our solution is purely software-based. So our secret sauce, the 3 key ingredients in our secret sauce is some machine learning plus some technique in measurements plus a bit of statistics. And by doing that, we achieve tens of nanosecond accuracy, and we are using purely software implementations. So please also check out our posters. Thanks.
Thank you for representing your fellow students for 2 posters. Now our next speaker is Stephen Yang.
Hello, my name is Stephen Yang.
Do we have your slide up?
Yes, yes. Hello, my name is Stephen Yang, and today I'll be presenting a poster on Nanolog, a nanosecond scale logging system that we built in C++. And it's a logging system that's 1 to 2 orders of magnitude faster than the competing systems out there, like Log4j2, Boost, or SpeedyLog, all while maintaining a fairly intuitive printf-like API. The system has a throughput of over 60 million log messages per second at a median latency of just 12.5 nanoseconds. For comparison, our closest competitor, Log4j2, only achieves a throughput of about 1.5 million log messages per second. And it achieves this insane performance by shifting work out of the runtime hot path into the compilation and the post-execution phases of the application. More specifically, it slims down the log messages at compile time by extracting the static components, outputs the log in a compacted binary format, and then relies on an offline process to reinflate the logs. And what this buys us is the ability to log more often, in more detail, and even do it in production where response times are critical.
Thank you. Our next speaker is Thomas Navidi.
Hi, so I'm working with the PowerNet project here at Stanford, and I'm going to be talking about specifically the cloud coordinator aspect. And basically the problem is we have a distribution network with distributed solar and battery storage resources. And the problem is, how do we optimize these storage resources in order to minimize the cost of operating this grid? And there's a lot of challenges in this problem. First, the stochastic nature of the solar, and also the demand of each house. Also, the information delays between the houses to our cloud coordinator. And also, we want to maintain power quality in the network. So our solution is to use 2 stages, a global optimization and a local optimization, which exchange information under strict delays. And basically, we tried 3 different implementations of this architecture with pretty interesting results. So come check out the poster for more details on that.
Thank you, Thomas. Our next speaker is Tom Chaperbrook. Did I even come close to your last name?
Yeah, it's Jatulaprik.
Excellent.
Okay. Academic choices made by students in college are important and have lifelong consequences. However, these choices are not observable by researchers for many reasons. So to solve this problem, we built Carta. Carta is a course exploration platform. It's a web application that combines 15 years of official Stanford student transcripts and also evaluation data to help students navigate in the college. And in return, we get to learn about how they make this choice. So we can observe about this choice. And if you want to learn more whether having access to more information can causally increase or decrease GPA, come check out our poster.
Thanks, Tom. Our next poster is by Will Hamilton.
Hi. So sentiment analysis, where we use machine learning tools to infer the emotion or attitude in texts, has a lot of important applications. So you can use it to predict whether or not a stock is going to go up or down, or social scientists can also use these methods to do large-scale studies of antisocial behavior. However, to really make sentiment analysis tools work at a state-of-the-art level off the shelf, they need to be aware of language variation. So you take the example of a word like soft. If you're in an online community about sports, if you call somebody else soft, that's probably an insult. Whereas if you were in a community about My Little Pony, calling something soft is probably a good thing. So come by my poster and I'll talk about some tools that I've designed to discover this sort of variation and also techniques I've developed to make sentiment analysis robust to this variation. Thanks.
Our next speaker is Yi Liu.
Good evening, everyone. I'm Yi from Professor Ada Poon's group. We are addressing the issue of the Alzheimer's disease, a common neurodegenerative disease among elderly people. Symptoms of Alzheimer's disease include worsening memory, difficulty in performing everyday activities, declined language skills and thinking abilities, and eventually death. Currently, there is no cure. In this project, we aim to retrieve memory in amnesic mice, which can be viewed as a model of early-stage Alzheimer's disease. We'll electrically stimulate the neurons to recall memory. We'll also build a time evolutionary 3D model for the memory consolidation process. To achieve these goals, we'll design and build fully implantable wireless implants for in vivo neural recording and stimulation. And we'll also use machine learning to build a model for the memory consolidation process. For more information, please come to my poster. Thank you.
Thank you. Our next speaker is Hng Yi.
Hello, everyone. My name is Yu Hang, and I work with Professor Edison Okamura. So my research is about using haptics, which is the sense of touch, to facilitate communication between human and robot. So we primarily focus on mobile robots that can follow people around, like this autonomous suitcase shown in the picture. So one challenge of such robotic system is that human environments are usually highly dynamic and have many moving obstacles. So these robots would inevitably get in trouble somewhere. To help solve this problem, we design wearable and holdable haptic interfaces and algorithms that enable bidirectional communication between human and the robot follower. If you're interested, check out my poster. Thank you.
Thank you. Our next poster is by Prateek Verma.
Hi, my name is Prateek. This work is on combining signal processing and deep learning for audio-speech enhancement. So deep learning had a profound impact on a lot of fields, and audio was one of them as well. So speech enhancement deals with using machine learning or neural network to improve the quality over the telephone, which can probably improve speech recognition or lead to better hearing aid design. A lot of people have been applying very, very large models for a lot of tasks. For example, like say 15-layer model or 10-layer model or 150-layer model. So in this work, what we have shown is we try to combine a traditional signal processing approach with a deep learning approach, and we design a very shallow network which is able to achieve state-of-the-art performance due to the fact that it is learning all the things from scratch. And to know more about, you can come to my poster. Thank you.
Our next poster is by McKenzie Weekley and Abe Davis, with special technical assistance by Connie Chen.
Research is about computational editing for dialogue-driven scenes. Filmmakers often record many versions or takes of a scene to capture different camera angles and performances. But editing these takes together with traditional tools is both difficult and time-consuming. We've built software that uses computer vision and speech analysis to align different takes with a common script, and automatically edit these takes together based on high-level specifications from the user, like use close-up shots for more emotional lines, choose faster performances to set a quicker pace, or put more focus on a particular character. Our system makes editing dialogue-driven scenes much more efficient, turning a process that takes even professionals hours of manual effort into one that takes minutes. Come check out our poster to learn more.
Thank you, McKenzie and Abe. McKenzie and Abe, just to be clear, if people come to the poster and ask you a question, you're going to actually talk to them, right? Okay, good.
So today I'm here to present my research on a couple of related and very interesting topics. The first one being, how do we basically build models which can be easily understood by domain experts, such as medical professionals or judges in criminal justice system. So the other line of work that I have, I'll be talking about today at my poster, is to basically understand how do we develop this automated decision-making systems from observational data. So both of these works are rather challenging because they involve kind of dealing with things like counterfactual inference, addressing some of these data points for which not all possible outcomes are available in the data. Please come by my poster to know more details. Thank you.
Thank you, Hema. Our next poster is by Tim Shi.
Good evening, everyone.
Is that you?
So this is a work between Stanford and NLP and OpenAI. The goal, there's a saying that the most likely place for general AI to emerge is the internet because of the massive volume of data available. So the goal of our project is to build an AI that could interact with web pages just like humans do, and once we're successful, also prevent it from taking over the internet. Our agent interacts with web pages and perceives it through pixels and DOM elements, and also perform low-level actions like keyboard and mouse. So it can do things like booking a flight on United.com, or making a reservation on Yelp, or using a mortgage calculator. We created a benchmark called WorderBits to evaluate the agent's ability to perform semantic reasoning and hierarchical reinforcement learning. And by training agent in WorderBits, we hope to develop an AI that could automate things you do on the internet. Yeah, thank you.
Thank you. Our next poster presenter is Sidat Wong.
Hi. So we want to bridge the gap between programming languages and natural language. So programming language is precise and easy for computers to understand. But because it has an uncompromising syntax, it is hard for people to produce. On the other hand, natural language is ambiguous and therefore easy for people to produce. But because it has such a flexible syntax, it's hard for computers to understand. We get a crowd of users to interact and build structures such as this bridge through a language interface. In the beginning, the computer only understands a programming language, and as people use it, they can teach the system through defining concepts, and the system can also learn from their actions. So in this approach, we use both data and a precise semantic grammar to naturalize a programming language.
Thank you. Our next poster is by William Shen.
Hi, everyone. My name is William Shen. I'm a CS undergrad working with Professor Silvio Sabaris. I'm going to talk about our most recent paper with Professor Silvio that is accepted to CVPR 2017. So feedback network is a project that studies feedback-based learning models and their merits over traditional feed-forward counterparts like ResNet. We discovered that feedback mechanism brings about 3 major advantages over feed-forward counterparts. And the first one is early prediction, as you can see on the top right. It means that since the output is in an episodic manner, we can retrieve early prediction in only a fraction of the total runtime. And the second advantage is taxonomic prediction. That means the episodic output actually naturally conforms to the hierarchical structure in output space. And so that means the earlier episodes try to tackle the high-level ideas, while the later ones go into the fine-grained details. For the third advantage and application, you can talk to me at the poster.
Thank you. Our next poster is by He Wong.
Yeah. So understanding human-object interaction is crucial for robotics and computer perception, while remaining very challenging in computer vision community. So in this work, we aim at learning a generative model of human-object interaction directly from video data. We first observed that the object state change is the consequence of human actions. So we model the causality behind the interactions, which is represented as the joint state change of human action, object state, and hand using LSTM. This gives us a plot of interactions. Then we feel the detail of the interactions by learning the moving trajectory and moving target distributions. In short, we learn from 2D interaction videos, and we generate new 3D animation of unseen interaction events.
Our next speaker is Pablo Paredes. He has no slide, but he does have a poster outside, right?
I do.
Very good.
That's why I'm here.
Pablo.
So I'm here to ask a question. Who here commutes to work? Who loves it? Yeah, very few. So we believe that a commute is a huge opportunity to actually change the way that life is perceived. Like Americans spend an hour of their days in a car commuting. And if we can change that into a mindful moment when you actually improve mental health, we can have like the ultimate sofa for psychologists. So everybody will sit in the same place twice a day, every single day. We can do very cool interventions. We're treating different ideas. Virtual reality, we're doing haptic stimulation of breathing. We're doing chatbots in the car. We're trying to see you dancing maybe in the car. We believe that the ultimate place for you to improve your mental health is the commute. So come and see my poster, conveniently located at the very end, so you have a long commute before you see me. Thank you very much.
Dancing in the car. Okay. Well, amazing. Please join me in thanking all of our fantastic students and postdocs. Mendel, Connie, any final comments, announcements, anything? Thank you all for your attention and contributions all day. Please enjoy our students, postdocs, and posters. Good night.